Hey guys, this is Terrence. Welcome to the third episode of RhinoPython and GhPython Playground. As I mentioned at the end of previous video, dealing with curved surface is gonna be today's topic. And at the first half of this video, I'm going to talk about how to divide a curved surface according to our own preference. That requires a completely different technique compared to working on the plans. And as we are doing coding here, we want to have a higher level of control on the overall object we are working on. And the second half of this video, I'd like to talk about how to pop the point from the surface. That requires us to compute the surface's normal vector on the specific position on the surface. And we can use that vector to move the point away from the surface. So let's get started. At first, let's quickly write some code to generate a curved surface. But before that, let's create a node called GhPython script. Double-click this, and this is the GhPython's built-in text editor. For sure, you guys can just write code inside here, like print a test. Then let's put a panel here. You can see the node runs the code you write in it. But my custom is to work in a discrete IDE, which is called Microsoft Visual Studio Code, because this IDE has a dark interface, which is good for my eyes, and the IDE is also an ideal place to organize a huge chunk of code. So I prefer to work in here and connect this Python file to this GhPython node. Then I can just write here and run the node here. The result will show up in the Rhino workspace. Let's see how to do this. First, let's right-click this and click this Show Code Input Parameter. Let's create another node called File Path. Right-click this and select one existing file, select our code file, connect this file path to the code input here. Here is an error, but you don't need to worry about that. Just right click, input is path. Then let's try if my file is successfully connected to the GhPython node. Let's say import RhinoScript syntax as rs and print hello Python. Save it. I will create another node called trigger. Connect this node to the GhPython editor. Then I can just run code here without opening this text editor. Let me do this. Okay. Our code is successfully executed in this GhPython node. Then let's start coding inside this IDE. Then let's define a function which is called create surface, which takes 4 parameters. X number equals to 10 by default, Y number equals to 10 as well, X step equals to 5, and the Y step equals to 5 by default as well. Then inside this function, I want to declare a start, start angle equals to 0, X period equals to 2 multiplied by pi. But before using this, I need to import the pi from the math. From math, import pi and the sine as well. I will use sine function to generate a series of points, then connect these points into a wavy curve. Then we can generate a series of this wavy curve, loft them into a wavy surface. This is the logic of creating the surface. Let's keep going. Y period equals to 2 multiplied by pi as well. Then we declare an empty curve list and loop over all the numbers, all the y numbers, range y number plus 1 points equals to an empty list. We are going to add point into this point list when we are looping over the x numbers. Range x number plus 1. Then inside this nested loop, we can start adding points into the point list. First, we calculate the angle step equals to x period divided by x number, and then points, append a new point with the coordinates x equals to x multiplied by x step. The y coordinate is y multiplied by y step, and the z value, the z coordinate equals to 2 times sine x multiplied by x angle step plus the start angle. Now we have a series of points. We need to connect all the points into a curve. Let's run this one. Let's do this. Curves.append rs.add curve. This is a RhinoScript syntax built-in function. Takes all the points we just generated, then the start angle plus equals to y period divided by y number. This is the angle step on y direction. At last, return a surface. Add loft surface, which takes all our curves. And we can try to run this function to see is there any error inside here. We can say surface equals to create surface. Now let's make it by default, and we should modify a name here to make this name and this name match. Then there will be a result showing up here. If there's no name match here and here, the result won't show up in the Rhino's workspace. We can change this to surface. Save this code and run it. Oh, we have this now. This is our basic surface. And let me explain this code a little bit. Like, when we loop over the x range here, x number here, we basically creating a series of curves like this. Then when we're looking over the y number, we just gradually adding the start angle step by step. Then we can create this kind of curve surface. You can try it yourself because it's quite hard to explain, but when you're doing it, you will understand the logic inside here. And then we want to have some control over the size, the dimension of this surface. I want to tweak on the x step and y step. Let me modify this step and y step here. And for now, these two values equals to 5 by default. I can add node. I can add like 10 for x, 10 for y, and input these two values into my surface. I can say 10 by default, and X step, Y step. To see if this is working. Okay. Now we can change the value to influence the shape we did in this RhinoPython node, a GhPython node. Then let's think about how to divide this surface. And we can take an example which we can see in many Grasshopper tutorials. We use the node divide domain, provide the UV value. The U value could be 10 and V value could also be 10. Then we use another node called isotrim to cut the surface. Now we have 100 subsurface because we have 10 steps in U domain and 10 steps in V domain. In this example, we can see that the factors controlling the curvy surface division are the U and V. But what are U and V? Let me bring up this sketchpad and draw some diagrams. I will use this to try to explain what is UV. Let's take a metaphor. Let's draw a planar surface. Draw a rectangle. Each rectangle has 2 dimensions, which is length and width. And in the NURBS surface, these 2 dimensions corresponded to the U and V. I mean, in a rectangle, we have length and width, but in a NURBS surface, no matter it's planar or it's curved, they all have the U and V dimensions. Then let's think about the width has its specific values. That is a distance value. Maybe in this example, we can say the width is 4 centimeters. The length is 5 centimeters. And the same rule applies to the UV domain. Let me change another color to show the UV domain. U has a range from a start to the end. It doesn't necessarily start from 0. Sometimes starts from a very weird number, but that's a very rare occasion. We can write some code to cope with that occasion in the later part of this video. And the V domain also have a start and end. And the end minus star equals to some number very similar to the length. Maybe here could also 5. But this 5 is not the length. It's a far more complicated definition. It is maybe the distance and the tangency. I'm still not very clear about how this domain represents. Now I only know how to work with this. Then if we want to divide the surface, we can just divide these 2 domains. Then point this domain, each of the domain to the surface. Oh, sorry. It's very stupid. What's going on here? Oh, God. Okay. Now, this is the point because we find this distance, we find distance, and we map the distance maybe 0.5, just example, maybe 0.5, and input this value to a function, to another function, another RhinoScript syntax function, which is called evaluate surface. then we will find this point. And how to divide this domain will affect how we divide the whole surface. If we have this, the end part wider and the former part maybe narrower, the surface will be like this. Maybe we have here and we have here, we have points here, but we have a point here. The domain will become unevenly divided, and we can achieve this by code. We can manipulate the way of dividing U domain and dividing V domain. Then we can use the division to control the surface's subdivision. And let's achieve this in our code. Let's define another function called divide surface, which takes a surface as input. Then first, let's check what is the U domain and what is the V domain of our surface. Let me declare U domain equals to, I want to make this two part wider, and rs call a Rhino script syntax function surface domain that requires two inputs. The first one is our surface. The second one we can look at here. When we run this function, we can just get one of two domains. If our second input is 0, we will get the U domain, and if this direction equals to 1, we will get the V domain. And for the U domain, we just type 0 here, and for the V domain equals to rs dot surface domain, and this time we input 1. Then we can print these two values. I want to make the result more clear. I will say U domain and show this U domain. We print another line, V domain, and show the V domain here. Save the code. Call this function. We just call this. We don't need to assign it to a specific value. Divide surface with our surface as input. Save it and run the code. Now we can see these are our domains. The U domain ranges from 0.0 to 50-ish, and the V domain ranges from 0 to 41-ish. If we change these values, change the shape of the surface, the domain also changed as well. The next step is we need to find a way to divide these two domains. And my solution is I will create a node called range. This node automatically generates a series of numbers ranges from 0 to 1 with the step 0.1. Now think about this. If we multiply each of these value, to this domain end, we will divide this domain into 11 steps as here shows. So let me do this, but first let me add two inputs. I call this U and I call this V. These two are basically UV divisions. I connect these two nodes here. Oh, sorry, I just created one, copy one and paste. But something wrong happens here. You can find this node actually runs 10 times because we still forget to change the value type here. We need to hover over the U, change the data type to list access. We do the same thing on the V. Then things goes back to normal. Now we have these two values, we can start to divide the domain. Let's remove these two print code and set u steps equals to u and u. This u equals to this u because these two files are now connected, and this v step equals to v. Then we want to have a lot of surface points. We use the technique we already used in previous two videos, which are create a surface a point dictionary. Then we just loop over the two steps for j in range length v step, and nested another loop I in range length u step. We retrieve the steps. Then we should retrieve retrieve each step on the I position and on the j position. So u pos v position equals to u step at location I and v steps at index of j. Now we can keep adding points to the point dictionary. We can say pt equals to rs at dot evaluate surface, like I mentioned several minutes before. We input a surface with the u value here and with the v value here. Then we add the point to the point dictionary. Surface points with the key I and j equals to the point. Save this code, and I think yes, we need to return a surface point here, surface points dictionary here. And here, assign this to the surface points dictionary, save the code, and add a new output, change the name to the surface points. Now, save this, oh, sorry. And use the trigger to run the code. Something goes wrong here. Let me take a look. UV, we have this. Evaluate surface, yes, we have this. Let me print this out to see if here's the result. Okay, I made a mistake, sorry. Save it, run it again. Oh yes, we do have surface. Oh, sorry, I forget the essential step. If we want to show points here, we need to use the add point function, add points, and we flatten this structure. We call list surface points dot values. Then we run it again. I believe we will have no, still no values. Run it. Something goes wrong here, sorry. We should add 2 lines of code to multiply this value with the domain. I forget this essential step. equals to u domain 0 plus u position multiplied by u domain index 1 minus u domain index 0, and do the same thing on the v domain. Change this to v position v, and replace these two values with current u and current v. I think this time it works. Now, some of you might feeling curious about why we already evenly divided the domain. The result still looks weird, and you can see these two parts are apparently wider than the inner parts. That's because the domain on the surface aren't evenly distributed. Somewhere could be larger, somewhere could be narrower, and we can fix this by adding another node, which is called graph mapper. We connect this into this graph mapper and reconnect this into the v input. Now we can just right-click this graph mapper, choose the graph type as Bezier. Then when we modify these curves, we can see all the points gradually scattered through the two sides of the surface. And we can see this graph mapper actually remaps the values generated in the ranges node. We can compare this. They already remapped. And now we can use this graph mapper to rearrange this point. We can also add this node to the U input. Then we will have a very freedom control over how the points scattered on the surface. If you want the central part wider, you can use this kind of type, and if you want this two sides wider, this edge size wider, you can choose to map in this way. Maybe, oh sorry, it goes too far. And here is, we use graph mapper to remap the point on the surface. We can still add another node. We can just add a number slider to control the number of points on the surface. Okay, sorry, this is domain. We shouldn't connect it to here. Connect to the numbers here. We can control the total number on the surface. I still want to go back to the evenly distributed pattern. That makes more sense, I think. And after this step, we already know how to freely control the point distribution on our surface. The next step is to draw polylines to divide this surface. Now let's go back to our code to write some code to draw the polylines, then divide our surface. And I want to add some code here. I can say if I is larger than 0 and j is larger than 0. And we append some, we retrieve some points from the surface point dictionary, then use the point to generate the polyline as what we did in the previous two videos. Like we first retrieve the point A, surface points, and with the key I and j, copy this 4 times point B, point C, sorry, and point D here. What's going on? Okay. And we want to draw the polyline counterclockwise. So the second point is ij minus 1. The next point is I minus 1, j minus 1, and the last point is I minus 1 and j. Now let's put all these points into a function. A function we are already very familiar with is called rs@polyline. Put all the points inside here: point A, point B, point C, and point D. Ends up with a point A. We should close the curve. And then we can declare a new variable called polylines equals to an empty list. We just append the curve to the polyline. We use polys.append here, then we also return these polylines, and here we just add some code. We also return it. We also assign the polylines to this variable, and we add an output here. We call it polys. Sorry for the polys, yes. And save it, run it. Something goes wrong again. Missing member exception. Values. Oh no. I place this polys to the wrong position. This should be here, and save it, run it. Oh, I just figured out what's going wrong here. Remove the white space and run it again. Now you can see we have these polylines. I want to add a container to highlight it. And if we change the graph here, all the polylines changed simultaneously. We can keep it still evenly distributed. And then let's go to our last function today, last part today, which is we want to move this point away from the surface to create the second layer of grid. Let's define the last function in this video. I call it normal point. And with the input surface, I will call a function called rs.surfaceNormal. Normal, and check its input that requires a surface ID, which is our surface, and a UV parameter as a list. Okay, so we just type UV here and we add an input called UV. And this returns a normal. I can say normal equals to this RS surface normal. Then we can just return this normal. And to see what's going on inside this function, I want to add a new variable here called normals equals to an empty list. And once I create a new point, I add the normal below. I add the points, the surface at the points the surface at the point locations normal. Add to the new list. I can say normals append yes, called normal point with the surface and the UV value. I should make it into a list. Input issue again. Okay, it's current U and current V. Now I'd like to return these normals here. Return normals at here. Add normals. And for the GhPython node, add an output called normals. Make them corresponded with each other. Run the code to see is there anything inside here. Okay, now we want to use this node called vector display to show the vectors we just created, to show the normals. For the anchor point, we need to select the surface points and vector. Oh, it's pretty small. And it's pointing down because we mess up in the UV direction. We should go back to our first function. At the return part, we need to add some code called reverse. Reverse the curves. And this means we need to reverse the curves list. Reverse the curves. Like at the beginning, we generate the curve from this direction. Now, after the loft, the surface's front point is facing down. If we loft the curves in a reverse direction, this surface will pointing up. Let me save this code and run it. Now we fixed this issue. Just add the reversed function here to reverse the curves list. And we have all the normals. We can use these normals to move the points. For now, we just need to add some codes here to add new points to the point dictionary. Now, for now, we want to have 2 layers of points. So we can add one more digit here to specify which the points belongs to which layer. Now, the point here belongs to the 0 layer, and we want to add this point with the vector and add this moved point to the new position, new index in the dictionary equals to rs.pointadd point1 and point 2. Yes, it accepts the 3D point or the 3D vector. Now we can take the point as the first input and take a normal. Now we separate these 2 parts. We can say normal equals to this function. Then append the normal into normals. Here point, and for the point add part, we add the point with the normal vector to see if this works. It doesn't. So 1 equals to rs dot. Save it and run it. Still doesn't work. surface point ij1 equals to rst. Key error in line 43. Oh yes, here is the problem. I already updated the keys, but haven't updated it into this part, in this part. Run it. Yes, we have our points now, and we don't need the normals. We don't need to show the normals now. We just remove it here and remove it here. Save it and run it. Now we already popped the point from the surface according to the normal vector. What we want to do now is to enlarge this distance. We want the point to move far away from the surface, and we should go back to the normal point function. We should add another vector, another parameter called amplitude, and we add the last parameter here, the last input here, called yes, amp. Make it simple and set it to 5. Yeah, I want to organize my Grasshopper map a little bit. It starts looking chaotic now. Move it here and move this here. We don't need these two panels, and move this down here. Oh, this could be closer. And run the code and save it. And what's going on here? Normal points take, yes, we haven't input this value into this function. We can do this at here, amp. Save it and run it. Now we can try to we just add the parameter. We haven't used it. The function we need to use is called normal.rs vector scale. That means we multiply the length of this vector, make the vector longer. We put the normal here and put the scale amplitude. Save it. Run the code again. Now these points are apparently far away from the surface. We can control the distance from this slider. Maybe if I change the slider into a decimal one, will look smoother. Okay, and the last step, the very last step, draw polylines on this second layer of points. Let's go back to the divide surface function, and down here at the add polyline part, I'd like to add a for loop for n in range 2, as we want to add 2 layers of polyline. This is the first layer, and up here this is the second layer, and replace the 0 with n for range n. Don't forget indentation here. Indentation in Python is very, very sensitive and important. And this means when n equals to 0, the code draw the first layer of polyline, and when n equals to 1, the code draws the second layer of polyline. Let's save this code and run it. I want to remove all the unnecessary displays. Only preserves these 2 layers of polyline. Yes, we have this. increase the number, slightly adjust the layout, adjust the distribution, maybe just it. And then we can add some nodes to loft these two layers of curves. I'd like to use split list at the index of list length. It should be dispatch this two layers of graph and merge them. Then loft it. Yes, and this is our result for today. We can change the amplitude. It goes lagging. But that's fine. I don't think this will recover in 1 minute. So let's just stop here. We will leave all the rest to the next video, to the next part. Okay guys, as you can see, the Rhino and the Grasshopper is still not responding, so we have to stop at here today. And this is also another long video. I feel so sorry about that. I always trying to narrow down the length of video, but I find it's quite difficult. I will try my best next time. And also, I feel so sorry for so many hiccups today, for the errors, for the PC issues, for the input issues, for that kind of issues, and this is also a challenging video for me because I have to explain so many complex concepts. I'm still trying my best to do better, and I'm keep learning from others, and I hope my future video will have a huge improve. And that's it for today's video. Thank you so much for watching. And if you guys have any comments, have any thoughts, or even critics, please leave your comments below, and I will really appreciate that. For the next part, I will talk about how to offset the curve, how to offset the polylines in this condition, and to make each unit become a solid object with the thickness. That's the next week's topic. And that's it. Thank you so much for watching. Bye bye.